If attach them together, we're considering attaching them together. We want to make sure they don't loosen. So there's a few things that people do in order to try to prevent loosening. One of the most common is a helical split type ring washer, as shown here. I want to emphasize those are basically useless. NASA has did an extensive study that was kind of released recently into that topic, and yeah, basically completely useless for actually preventing loosening. So don't use those. Twisted tooth type. Basically, when you tighten it down, it has these little teeth that kind of deform and kind of bite into each side. So those can help to a degree. We got castle nuts. So basically, these are nuts that have slotted nuts and castle nuts. For the slotted nut, basically you kind of just cut a groove into the nut itself. For the castle nut, the nut itself, the main body of the nut doesn't have any grooves, but it's got this little extrusion here where it's got these basically slots have been built in, and then you can insert a cotter pin into a drilled hole in the bolt. So that and then once that's tightened up, drill the hole into the bolt. Obviously, this at the point that you're installing it, the hole would be in the portion of the bolt that is kind of it's past the stressed portion, so you're not drilling into any parts there that are seeing any major stresses. So the fact that you're drilling a hole there isn't exactly like reducing the the fatigue strength or anything like that. Other ones that we can see here, so we can have nylon inserts that you can insert, kind of stick into the kind of in between the surface, the bolt, kind of into the surface, kind of around the bolt, and then the nut comes on top. Usually, you'll have a little space here that it can kind of deform into. So when it's compressed, not only does it kind of the high friction from the nylon is going to prevent loosening, it also provides some sealant as well. So not necessarily nylon, but nylon's going to be the most common. We've got a spring nut here. So basically this one, the nut itself is kind of cut such that when it's tightened up enough, it deforms. So basically, when it gets tightened, you're going to end up with it doing like this. So it's going to be kind of squeezing, pinching at the top, basically. So it pinches at the top, pinches into the threads of the bolt, this portion here, these portions here, kind of dig into the surface there. So that'll that additional kind of friction coming in there is going to reduce your loosening. And then this is basically a single thread nut. So basically, these little prongs here, you insert the bolt through them, and then they just pinch down when the nut is tightened enough. So you'll kind of feel it, because you'll see a fair amount more resistance than you started out with. Again, it's used for quick loads, quickly applied, and for light loads. Obviously, something like that wouldn't necessarily be able to sustain a lot of force, but So these types are typically going to be spinning freely until they're seated, and then you're going to see more resistance in the torsion once it's tightened down. And that's again due to some sort of deflection that occurs when the nut's tightened. Other types, basically it's going to have some sort of counteracting torque the entire time, even if the joint is still loose. So this one here, it's basically kind of a tapered nut, and where kind of like these kind of, so it's got these grooves cut into the top of the nut, and those portions are tapered, so that kind of as you're screwing the bolt into the nut, once you start screwing it in, those portions there are kind of clamping down on the nut the entire time. So that again reduces your the friction caused by that normal load is going to be reducing the loosening that might otherwise occur. Some other ones are going to have different types of nylon inserts, color or plug, that basically acts on the bolt threads the entire time, or at least once it's been inserted past this point here. And then we got a distorted nut. So these ones kind of come they kind of come pre-squeezed out of shape a little bit. Honestly, I'm not sure if that's how they make them, but that's kind of the effect. And then basically it's the force exerted on the nut by the bolt as you try to screw the nut into the bolt that forces the threads, that forces the nut and the threads and the rest of the nut into a more circular shape. So because otherwise it would be it's being deformed by the presence of the bolt, so it's clamping down on there, and again you're getting a friction grip on the bolt threads as a result. A quick and dirty method: a jam nut, an additional nut that you can throw in there just to prevent the first nut from loosening. Again, quick and dirty, not necessarily something you want to rely upon for a long-term application, but it can certainly help. And then, of course, if you want to make this kind of make go for the Cadillac solution, thread locking. So an adhesive that is basically applied to the threads of the bolt or the nut, I suppose. It can be done manually, and then basically insert, and then it the adhesive kind of sets and will hold your bolt into place. Obviously, this kind of makes it less of a easily removable, but that's kind of the point. If if you're using this, then you want it to, you don't want it to be quite as easy to be removed as you might as some others. Still, again, they can be removed. You just kind of gotta, you're not necessarily going to be able to do so in a simple fashion, but it can be applied manually. There's sometimes you can get some where there's capsules installed in the nut or the bolt. I believe typically in the nut, but I'm not completely sure. And basically, as you insert the bolt into the nut, the capsules will kind of get in the way, and then you force it a little bit, the capsules burst, and then they'll leak the adhesive all over the threads as you insert it, and then that'll provide good coverage, and then you tighten it up, and then it locks up, and then you're good to go. So we're talking the bolt failure in shear. So again, this is kind of this is a value that was arrived at after a fair amount of experimental study. So based upon direct shear of the unthreaded portion. So kind of like what would be going on here. Um, so we can usually expect there to be failure when the shear strength in the unthreaded portion hits 0.62 of the ultimate strength of the bolt. And of course, that'll be those strengths will depend upon what sort of grade of bolt you're using. That having been said, you may be designing for no yielding instead. So a common failure criteria is using the proof strength, the von Mises equivalent of the proof strength as your failure criteria. And typically speaking, so basically when you're applying some sort of kind of shear load or torsional load on the kind of the bolt joint, you're going to get some relaxation. There's going to be some relaxation in the tensile strength of the the tensile load in the bolt after tightening. So you're going to tighten it up a little bit, and it's going to you typically expect it to relax a little bit. That torsional load that is kind of applied at first determines kind of the force in the bolt, and the force in the bolt determines what sort of friction we can expect to see in that joint. So basically, we're typically not going to be relying upon only the shear strength of the bolt. Oftentimes, in fact, we're trying to be designing our joints so that the frictional interference between the components that we're clamping together is the only thing that carries any shear load. So that's typically more ideal than relying upon the bolt itself to avoid failure, especially because at the very least, if by the time you get to loading it up enough that the bolt itself needs to carry some of that shear, then you've shifted. You'll have moved the components relative to one another at least a little bit, because otherwise there's going to be nothing, causing there's going to be no kind of capacity for that load to be transferred to the bolt. But anyways, okay, for an example, we've got this bracket here. We're assuming it's rigid. We're applying a load to it, and we want to determine what size of bolt we need in order to hold this thing safely. So with a particular safety factor, let's go for a safety factor of 6 with respect to the proof load. So relatively high safety factor. So we got two aspects of this. We got the load that is applied. So there's going to be some shear on the bolts, not necessarily the bolts themselves, but some portion of that should be carried by the friction. And we've got the tension that is going to be caused by the tendency of this load to cause the bracket to kind of rotate. So kind of it's going to want to it's got an out of plane moment being applied here. It's going to kind of want to cause rotation, which is going to cause those bolts to want to stretch out. Oh, sorry, this is going to cause those bolts to have to stretch out, at least in order to resist that rotation. So the first aspect that we're going to look at here is the kind of that stretching. So we've got So we've got the bracket here, we've got a load being applied, and again, it's going to basically, when measured, kind of, when this load is applied, at any point kind of measured at the wall, it's going to be causing a bit of a rotational moment. Now, kind of the point we were worried about here is the fact that, if it was trying to rotate, say, about this point, then what would happen there is that all this material down here, that would be jammed into the wall. So it's not really going to do anything. If it was rotating about here, same idea. All this here would be jammed into the wall. So we're kind of worried about what's happening if it's going to be rotating about point A. Because it can rotate about the bracket itself can rotate about point A without the bracket needing to deform. Now, as a result, basically that would cause, in order to prevent that rotation, we would need to cause some sort of reaction from the bolts holding stuff on. Now, since we're rotating about A, basically kind of the deformed shape is going to be something like this. So the strain that would be induced in the bolts is directly proportional to the distance from A. So we've got the one bolt down here, we've got the two bolts up here, and the force in this bolt, we'll call that FTE. F, tension at point for bolt E. Let's see, we've got E here, and we've got two of them called D up here. So if the force in FTE is a certain amount, then the force in the tensile force in the D bolts, each of those is going to be 4 times as much, because the displacement from A is 4 times as much, so it's going to see 4 times as much strain. So FTD is equal to 4 FTE. So now we've only got kind of the one unknown for forces, and we can just solve for what that would need to be in order to resist that moment. So if we take a sum of our moments about point A, that is going to be equal to the moment caused by the load. So that'll be a negative moment because it's a clockwise rotation it's going to be trying to cause. 24 kilonewtons times 500 millimeters, or half a meter, that's going to give us 12 kilonewton meters. And then, so negative, can't forget my negative. And then the bolts themselves are going to have forces as well applied to the bracket, and those are going to hold it onto the wall. So there's going to be positive moments because, again, taken about A, those are counterclockwise. So first, the one for FTE, got 100 millimeters times FTE, and then we're going to have the forces for bolts D. So again, there's 2 bolts, so I'll just throw a 2 in front of there, times FTD, which again is equal to 4 FTE. So 4 FTE times the distance, which is our 400 millimeters. And all that jazz is equal to 0. So grouping stuff together, 100 millimeters plus 2 times 4 times 400 millimeters. That gives us 3,300 millimeters FTE minus 12 kilonewton meters is equal to 0. And then we can solve for what FTE is. That's going to be equal to 12 divided by 3.3 meters. Obviously, we'll translate the millimeters to meters so that they cancel out with the meters on the kilonewton side. That gives us 3.63 repeating kilonewtons. So if we want to solve for what FTD is, we multiply that by 4. And that gives us 14.55 kilonewtons. So yeah, 14.55 kilonewtons is going to be kind of the tensile force that the bolt would need to be applying to the bracket in order to resist that rotation. Now again, that can be just the force in the bolt. It doesn't necessarily need, like if the initial tensioning is that amount, then we're good. It doesn't necessarily need. This doesn't necessarily need to represent an additional external load that's applied after the fact. But we do need, at least for our bolt, to be able to withstand this amount of stress. And we're working with a safety factor of 6 here. So if we want to be able to withstand this amount of stress, then how we calculate our stress. Our stress is just the FTD divided by our threaded area. And then if we multiply that by our safety factor 6, that needs to be equal to or less than our less than or equal to our proof strength, or SP. So just looking up what our proof strength is for that particular type of that grade of bolt. Just go back to our chart here. So we are working with a 9.8 class bolt. So we're working with a proof load of 650 megapascals. So 650 megapascals is our proof strength. So from there we can solve for what the minimum amount of our threaded area, our stress area, would need to be. So our AT needs to be greater than or equal, greater than or equal, our minimum AT is equal to our FTD times 6 divided by the 650 MPa. So that'll be equal to 14.55. Here, let's 1400. Let me think here. I'll erase that comma there. 14,550 newtons times 6 divided by 650 MPa. So again, I'm going to reformulate that in terms of newtons per millimeter squared. Newtons cancel out, obviously. The millimeter squared would move to the top. So that gives us a minimum threaded area, or a minimum stress area of 134.3 millimeters squared. So what size of bolt would we need in order to kind of meet that criteria? Well, going up to here on our chart, we would need, regardless of whether or not we're working with a coarse or a fine thread, we need at least a 16 millimeter diameter bolt. So 16, if we're looking at a coarse one, it's got a stress area of 157 millimeters squared. So 16 millimeter coarse as 157 millimeters squared AT. Okay, so that's the tensile portion. Now, for the shear stress, the shear load, we need to take that into account too. So essentially, worst case scenario is that the entirety of the load is going to be carried by the shank itself. If it does start to slip a little bit, it'll be carrying the shear load will be carried by that. So what sort of load are we talking about here? Well, if we go back up to here, and essentially we're looking at kind of the shear loads that would occur. We are going to have the direct shear, and we are going to have a bit of a torsional load. Shear caused by the torsional load, because basically again, similar to what we saw with welds, the assumption that can be made is that the direct shear is shared equally amongst all the welds, whereas the torsional load is carried shared equally amongst all the bolts, whereas the torsional load is basically divvied up in a manner that the forces generated are proportional to the distance from the centroid of the bolt area. So basically, similar to what we saw with welds, similar to what we saw with just the shaft. It's going to cause a tendency to kind of rotate about the centroid, and the amount it wants to rotate, so like the actual distance it wants to rotate, is going to be proportional to that distance. So the amount of force that needs to be generated by each bolt to resist that is also proportional to that distance. So the distance between those two bolt groups is 300 millimeters. Again, remember that E here was 100 millimeters from the bottom. This one was 400 millimeters from the bottom, so that distance between them is 300 millimeters. There's two of them at the top, one of them at the bottom. So the centroid of that weld group is going to be located on the center line here in the middle, and it's going to be located 100 millimeters from the top group, or 200 millimeters from the bottom bolt, like that. Now, this bracket, it needs to be in equilibrium. So if we take a moment about this point, then let's call that O, moment about the origin. If we take a moment about that point, it needs to be resisted. Essentially the what am I trying to say here? The forces that are the reaction forces that are generated need to be enough to resist to come up to a total moment of zero. So sum of the moment at A is equal to 0. So obviously the load and the fact it's off center from that centroid is going to cause basically a torsional moment. So that'll cause forces that will arise directly in order to counteract that torsional moment. And those forces that are going to arise are going to be, again, directly proportional to the length of the vector from the origin to the bolt in question, and its directionality will be perpendicular to that. So this thing is going to want to rotate here, so the forces that the bolts are going to be applying to the bracket are going to cause a counterclockwise rotation. So they're going to be doing this. And then we've also got the vertical load. So you got to remember they're equally sharing that vertical shear. So if this thing's pushing down, then there's going to be an upward reaction at each of the bolts. And the magnitude, again, it's shared equally, so the magnitude of that is 8 kilonewtons, 1/3 of 24 kilonewtons. But what is the magnitude of this reaction ones? So again, we know that the magnitude of that force is proportional to the distance from the center of proportional to the distance from the centroid. So this E1 here, that is 200 millimeters from the centroid. Whereas we got a certain radius here between the origin and these two D's here. They're the same distance away from the origin, just obviously different directions. And that radius is going to be equal to, again, just we're using Pythagoras' theorem, so 150 millimeters squared plus this 100 millimeters squared, which is equal to 180 millimeters squared. So the E here is a bit further away from the centroid, so it's going to be a bit larger. The force that's generated to counteract the moment is going to be a bit larger than the force that's generated at D, and it'll in proportion to it. So we can figure out what the ratio of those is going to be. That FE, I'm going to say FSE, F shear E is going to be equal to 200 millimeters divided by 150 millimeters of the F shear D, FSD. So 200 divided by 180, 1.11 repeating FSD. So now we got both forces, both the reaction forces in terms of one another, so we can solve, we can figure out what that is by solving for this equation. So the sum of the forces about the origin is equal to 0. Sorry, sum of the moments about the origin is equal to 0. So 0 is equal to the 24 kilonewtons times the 0.15 meters, 150 millimeters, 0.15 meters. So it's, and again, that's a clockwise rotation tendency, so that'll be negative. So negative 3.6 kilonewton meters. And then each of these are going to be applying counterclockwise rotations. So that'll be, we'll start off with the two FSD ones. So 2 times FSD times that distance, the 180 millimeters. And then we add the rotational moment caused by FSE. Again, solving for FSE in terms of FSD. So 1.11 repeating FSD times its distance from the centroid, which is the 200 millimeters. So all that jazz is equal to 0. So 3.6 kilonewton meters, move that over to the other side, is equal to, now it's equal to FSD times 2 times 180 plus 1.11 1111 times 200 millimeters. So that'll be 582.82 millimeters, or 0.5822 meters. So we can use that to solve for what FSD is. So that will be 3.6 kilonewton meters divided by 0.5822 meters. Meters cancels out, gives us 0.618 kilonewtons. So let's figure out how those vectors combine then. While we're at it, that times 1.11 will give us our FSE. .87 kilonewtons is our FSE. So let me just scroll up here for a second. I'm gonna copy and paste that again so I can draw on it. So at E, we've got the bolt is applying a vertical force of 8 kilonewtons, and it is applying a horizontal force of 6.87 kilonewtons, which is going to give us a resultant of 8 squared plus 6.87 squared. Take the square root of that. That gives us a resultant of, well, that gives us a resultant of 10.54 kilonewton. On the other two, however, again, we've still got the bolts applying a vertical upward force on both, but this one here, it's applying for those are for the direct shear, again 8 kilonewtons. The one on the left here, it however is applying force in this direction of 6.18 kilonewtons. So these cancel out somewhat. If we move this one over to here, we're getting a total vector that's going to be smaller than what we get on the other side, because we're applying, because this one has its vector perpendicular to the vector from the centroid to there. So these ones add up constructively. So 6.18 kilonewtons. So in order to find out what that is, again, we need to break up this 6.18 kilonewtons into its horizontal and vertical components. So again, you'll recall that this was 150 millimeters and 100 millimeters, and then 80 millimeters. And we know that the vertical portion of that force is going to be proportional to the horizontal offset, and vice versa. So the vertical portion of that is going to be equal to 6.18 kilonewtons times the 150 millimeters divided by the 180 millimeters. 6.18 times 150 divided by 180, that gives us 5.15. And then the horizontal portion of it is similarly 6.18 kilonewtons times 100 divided by 180. 6.18 times 100 divided by 180, that gives us 3.43 kilonewtons. So the vertical portion combines with the direct shear. So we got 5.15 kilonewtons, and we got the 8 kilonewtons here, and then we've got the horizontal portion, 3.43 kilonewtons, and that'll combine into a total vector that we can solve for by, again, Pythagoras shows up. 3.43 squared plus, let's see, 50, that'll be 13.15 squared. Take the square root of that. That'll give us 13.59 kilonewtons. So that's the shear load that bolt needs to, that bolt group needs to be able to carry. So, working under the worst case scenario is basically if the thing's not tight enough, then it's going to slip, and all the shear needs to be carried by the shank. Now, again, I would specify that is the shank. That is not necessarily going to be the threaded portion. So what we need to do here is we need to basically take that load and figure out and kind of combine it with the tensile load, and find out that so basically in the shank portion, if we're applying a shear and we're also pulling it, so the amount of the shear load that we're let me think here. I'll draw this. So we're applying a shear kind of in that is acting parallel to the plane of cutting transverse to the length of the bolt, and then the tensile load that we're also applying. So the tensile load, again, worst case scenario is in both cases on this bolt. It's for the top for the out of plane loading condition. It's the top two bolts, and for the shear one, it's the bolt on the top right. So in both situations, we're most worried about what's going on for that bolt. So we've got the shear load of the 13.59 kilonewtons, and then the tensile load that we were trying to attain was what? 14.55 kilonewtons. Okay, so we got the shear load, we've got the tensile load. So each of those can be converted to stresses by basically dividing by the area, the cross-sectional area, but we don't know that yet, so we'll just kind of throw in a nominal. So our shear stress is equal to 13,590 newtons divided by A, and our tensile stress is equal to 14,500 newtons divided by A. Same area. And then we can go ahead and use the formula to convert this to a von Mises equivalent. So basically we have our von Mises equivalent is equal to square root of the stress squared plus 3 times the shear. So that'll be equal to square root of 14,500 newtons divided by A plus 3 times squared. Can't forget the squared. Oh, yeah, I forgot the squared on the on the tau up here. Plus tau, so our 13,590 newtons divided by A squared. So obviously we can factor out the newtons per A. Because it gets squared and then gets, square root gets taken. So newtons per area times the square root of plus 3 times blah blah blah. Okay, so we got that. We're working with sorry. Got that. We let's see. So that gives us a von Mises equivalent stress of N over A times, newtons per area times, oh wait, I forgot to take the square root. I suppose that would help. Times 27,646. So, yeah, 27.6 kips per unit area is our von Mises equivalent stress. Now, if we're still going to be designing for the proof strength, a safety factor based upon a proof strength of 6, then 6 times the von Mises equivalent needs to be equal to, it needs to be less than or equal to our proof strength. So again, what's our proof strength here? We are working with what was that? Our SP was 650. 650 megapascals. So plugging in what we solved for the von Mises equivalent, and then we got 6 times that. So solving for A, six times 27 kilonewtons divided by the 650. Again, MPa, I'm going to convert that in newtons per millimeter. So our newtons cancel out, our millimeters moves to the top. And what do we have here? 26,646 divided by 650. that means that we have a minimum area in the shank of 255 millimeters squared. So we can, we know that the cross-sectional area of a circle is going to be equal to A is equal to pi. Why did I say? Well, pi r squared, or in terms of diameter, pi over 4 d squared. So we can solve for what d is. So our d needs to be at least 255 millimeters squared times 4 divided by pi, square root of that. So 255 times 4 divided by pi, and then the square root, that gives us a minimum diameter of 18 millimeters. So essentially we need to bump up the size of our bolt, basically one standard sizing up from what we had previously calculated for our in the last step, which is not terrible, and that's again based upon kind of the worst case assumption that the joint has basically loosened completely under the loading and loosening, and none of the shear load is being carried by friction, which is generally not going to be the case, but it's I guess it depends upon what you did in order to try to prevent loosening in the first place. So 18 millimeters would be a good, reasonable sizing for that bolt in order to attain our safety factor of 6 with respect to the proof strength. Now again, you may be wondering why I use just the A instead of the AT here. Again, keep in mind that the shear load doesn't occur in the threaded section. When we look at the bolt here, let's see here. When we look at the bolt, when we look at kind of like side view of the bolt here, the shear, that's occurring right here, not over here. So over here, we're worried about the tensile failure, whereas in this section we're worried about the tensile and the shear. But we can work with just the straight nominal diameter size of the bolt in the non-threaded section. So we're basically we're using a larger effective area for that cross section, which is good. All right, that's it for now.